All right, so welcome back to session two. We have around approximately an hour left before we conclude um, this part of mass moment. Excuse me, this part of mass moment. Um, I'm just checking. Yeah, okay. So what we touched on was the concept of what mass moment was, right, and the radius of gyration, and obviously we looked at some different axes over here, right? Again, very important. Make sure you're able to use that table on C15. This was supposed to be a sweet exercise here, and um, and the purpose of this is basically to establish which one of those bodies will roll down first. And if you assume that they all have the same mass and radius, you would have actually find that a solid sphere has the least not the solid sphere, yeah, the solid sphere has the least amount of mass moment of inertia compared to the other shapes. So that's quite interesting, but obviously I didn't actually end up doing that. Nevertheless, there we go into. So all of that was just warm-ups, just some foreplay to where we actually need to be. What's typically going to happen in a test type situation are the following things, right? You're going to get a combined shape of something like that, or something like this, or something like that, or something like this, something like that. Combined shape with parts missing, different types of material, or something like that. And you are required to obviously compute the mass moment of the whole assembly. And the next one would be to find the radius of gyration, obviously, to find the percentages of what contributes what to the mass moment. You would do that, and also the torque required to accelerate a particular thing. So I'm gonna obviously we're gonna redo this in the next session or whatever, but I'm just talking to it now so that you're aware of what type of stuff you need to obviously expect. But obviously we will do at least around 2 to 3 questions now. All right. So this is the first one. Okay. And this is where we start combining. I'm also making aware I've put up a table there of different densities, and I'm hoping to use this in your upcoming test where I will give you either this table to find the densities or give you the value, but obviously put it up there so you guys can have an overview of different types of densities of different metals, of whether it be ferrous or non-ferrous in particular. So let's not waste too much time and get to what we need to do. So this is the first question, right? So what we have here is, let's say the wheels are okay. So we need to find the mass moment of this whole assembly, right? And we have two discs at the end, wheels, um, which is made of aluminium, and in the center we have a, an axle which is made out of steel for that density over there, right? So I hope you all can picture this. Can we all picture what this looks like? I had some kind of image which I wanted to just check. Okay, cool. I'll just get a sketch for you. What this looks like, a bit of three-dimensional view. Can we all see what this looks like? Yeah, just place that there. Cool. I guess not everyone. Something like that. Yeah. Can you guys see that? Just ignore the other lines and stuff. So you've got two. Imagine like a weight. When you're lifting a barbell and there's two weights on the end. Something around that. That's the kind of object we kind of trying to analyze here. Don't ask me about this practical application, because clearly it's. Can you guys see that there? Yes. Cool. Nice. Thanks, Jared. So I'm just gonna prepare our example here on the blackboard. then we can actually just start with this. So the aim is to compute the mass moment of inertia. I've posted up all the notes, so you're gonna have an idea of what's expected of you. Let me just paste here. I need to get used to this new board. Okay, cool. Just give me a moment. Just take this. So what we're typically going to get is a shape which is combined and of different, different types of material. This is the common thing, and this is what I'm showing you is like the typical general approach of solving these problems. Most of them is going to end up being like this, but obviously we have different variations and stuff. But yeah, anyway, so the first thing we do is obviously let's first get the mass of everything, because obviously to compute the mass moment of inertia we require to we require to get, we need the mass to get the mass moment. As I'm just reading the question, what the question is supposed to say is that obviously the rotation is happening through that axis here, I don't know what we can call that, through the center here. Jeez, man, what's going on there? Okay, let's just see. Oh, it adds this weird tick thing. Oh, it's supposed to be like a tick. Honestly, I don't know what's going on there. That's weird. Okay. Center. Yeah, so we're rotating through there. So the first objective, and I just want to show you what we're working towards here, is this. That's over here. So what we're looking at is, I don't typically ask to work out a table, but we're going to have to work at the mass. We're going to have to work at the mass moment, and what is going to be nice is to work out the percentage of what contributes, percentage of the mass moment of inertia of the total, which contributes to basically what part, which was it, is the axle or the wheels which contribute to basically the mass moment of inertia, or which contributes the most. Sorry, that's a very important question which I'm going to try to include as well. So I'll probably attempt to create a question like that. Cool. So let's do this. So the first thing, let's find the mass of the wheels, right? The mass of the wheel, so MW, so it'll be density times volume. And we know that the wheels are made of aluminium, so that's 2,600. And what is the volume for a disc like that? We'll keep down. Seeing if you guys know your shape, you're supposed to be knowing this. I find it shocking that people do not know. Mudanalo. What is the volume? We find the volume of that wheel. So maybe I should sketch him here. So first object is this over here. So it looks like that. Yeah, well, okay. Does all the work for me, it seems. Just kind of push that my whiteboard doesn't do what I want to do now. Okay. So that's my one wheel. Okay. So can you guys please tell me what's the volume of this thing? Yeah. Pi r squared times depth. Yeah, that is fine, but that's the one I'm looking for. Yeah, I actually got the one I want. So, but remember, we have a hole in the center there, right? As you can see there in the sketch. So it'll be pi over 4 Let me just change this quickly. I have to leave this now again. 504, and that's the big diameter, which is 400. So 0.4 squared minus the one in the center over there, so 0.05 squared. Right. And then the depth would be the 70. I hope you guys agree with me here. So that's the total. Just saying, I hope you guys know that. Obviously, this is high school level type stuff. That is our mass. Now, Shanique, can you get the mass? Do you guys agree with that? So it's the diameter is 400 of the wheel. And this guy over here is 50. Oh, obviously the axle fits in there. Fantastic. Okay. This is super important. Like this concept, you just literally gonna apply this whole, well, not the concept, this procedure will be applied to just different types of objects and stuff and different, yeah. Thank you, Jared. He's got the answer there. You should get 22.51 easily, right? And obviously this is for one wheel. Yeah, that's fine. Okay, thank you all. So as always, got an extra decimal for us there. Okay, so for the next one is the model section, which is the axle. So we can just note that as MA, right? Very important. It's also mass density times volume. In this case, the axle is made out of steel, right? It states an axle is of steel, right? That's the center. The center, the piece joining. So it's just a rod would do something like that. Must be careful when I call it a rod. It's fairly, it's quite thick here in this case. So it's 7,800. If you're wondering where I'm getting these values from, these values are given here within the question. Like I said, you might get a table, but I'll probably have to make a small tutorial for you guys with the stuff. That's what I was planning to do anyway. And in this case, it's straightforward, so it's going to be pi over 4. Can someone just give me the remaining stuff here? I don't want to say too much. I want to see if everyone knows. Just zoom in. Just get to that picture. By the way, this is in your notes I've shared with you, so you can actually just find it there. Okay, is anyone going to give me that? Guess no one's going to do that. So the diameter is 50 mil, and we times that by 0.8. Right. Let's get the mass of the mass of the axle. Yeah, fantastic, Mr. Silver. 12.25. Is that correct? Doesn't seem. Axles should be 14.4 apparently according to our answer, and it should be more. It's more denser. Am I making a mistake somewhere? I think I know the mistake. Guys, what is the mistake? What am I missing? Be careful, don't listen to me, don't trust me. What am I missing here? It's obvious. Is the length 800? Yep, it's 70 times 2. Exactly, that's what we're missing. So it's 800 plus 70 times 2. I must, otherwise I think we'll just fall down. So this has to be adjusted. Just forgive me with this. So our total length is 800 plus 70 times 2. Cool. So it's 0.94 actually. Yeah. There we go. Sorry about that. So let's see. Yeah, I should get 14 point. There we go. 396. Beautiful, guys. Guys, we're doing this. And like this was something like this. This might either be 1 mark or 2 marks. It depends on the nature of the question and how many all in all how the question looks like. Sometimes it's 1, sometimes it's 2. Depends. Cool. Now, once we have the mass, right, as I said, and obviously this is for one axle we find, we've got for the wheels. We need to find the mass moment about that axis. So obviously it's rotating in that center there. So we need to find the mass moment of, we're going to find it of one wheel, and let's find out the axle. So go to table C15 and go find me those formulas. Go to table C15. Tell me the formula for the wheel, and tell me the formula for the axle. Be aware or cognizant of the rotation of the axis of rotation. So go find me those formulas. All right, okay, let's see. Tashriq. Yep, that's definitely correct. MD squared divided by 8. I agree with that. Through Z set, that's perfect. Obviously, don't we have to modify that? Are you sure about that? It's a disk, right? But it has a hole. So are you sure it's MD squared? What's the other one? Let's quickly see. Yeah, so you have to, no, it's not subtract smaller d. There's something else. Just have a look. So you write to that one. Look at the next one. So you're on the right track there. It is MD squared, but it's not. Just look at the next formula. Yeah. See, what's it? MD squared over 16. For which one is that? I mean, we have the. So sorry. So you see it for the wheel. Okay, for the disc. No, for the disc it's MD squared. Right, for the wheel. Sorry, for the axle it's MD squared. This is MD squared over 8. Right? And then for the wheel, what is it? It's in your face there. Ring, wheel. You got it. What's for the wheel? I'm waiting on you guys there. 0. Mr. Solver, Nosipo. So, guys, we have on the sheet a hoop and a ring, right? Obviously, a hoop, you're not considering that thickness over there, right? So, it has to be the ring. You guys got that? So, the formula for this one would be MD squared over 8. You guys got that? And I said beware of the axis of rotation, so that's fine. Even content to that. Any debates? Yes, okay, he said he's happy. Alex Horn is happy. Hey man, what am I doing? Whiteboard. Why is my whiteboard? It just decided to go away now. Okay. Yeah, there we go. Is everyone pleased with this before I move on? It's very important that you understand that. And we are rotating through the ZZ axis, so that makes sense. If I were to rotate it through the X, through the other way, it would be a different case. But obviously, I said it's rotating through there. Okay, and Super says yes as well. Fantastic. Okay, so next step is to compute um, our mass moment of inertia. Okay, so let's do that. Is it rotate from Z? Yes, it is rotate from ZZ. Yeah. So obviously, in this case, it's not telling you, but I'm telling you rotating through that center. So obviously, you have to look at the object and you can see. Because if it was rotating, let's say there, for instance, it will be something completely different. That way, out of set. So, but obviously, just it's rotating as per normal as we know. Sometimes it's not so tricky normally, but yeah. Yes, for complex shapes. Yes, Tashirik?
So would you always get something practical like the wheel with a shaft in the middle, or like will we sometimes be thrown off like say like maybe a wheel with like a different shape in the middle? Because I'm just thinking now if we had the wheel and we
Yes.
calculated that mass moment, and if we subtract whatever mass moment that the missing piece would have caused, would you get like the same
You,
answer? Or
you spot on. So let's quickly try and do that, eh? And I'll show you. Yeah, yeah. And your question is, if you look at the rest of the slides and the other examples, you'll see it's how it is. The only thing that we really add on this concept now, I'll tell you now, is that we typically want, or what happens if you're rotating away from this axis. So let's say XX and you want to rotate it AA. There's another formula that comes into play to figure out if you're rotating away from the axis of rotation. So you have to account for that extra height. But it's once we go through a few examples, it'll come out. Let's try the two ways, right? So here we're assuming it's a ring, and here we're assuming it's a thing, what we call this. It's a perfect cylindrical. If we're all happy, then we can move on. So for this one, a mass moment for one wheel is 22.513. 0.4 squared. Just give me a moment. I'm just bring in here. Plus 0.05, I think. Yes. Divided by 8. And if we get that, you should get 0.4573 kilogram meter squared. Very important. Thus, the mass was, what was the mass again? 14.396. And the diameter was 0.05 squared divided by 8. Okay. And let me just work it out. You should get 0.004, say 45, right? As you can see, the axial, if I'm correct, is providing a small amount of mass moment of inertia. Mass of the axle for the volume it is 0.49 or 0.94. What is that? The mass is of the axle is 14.396 kilograms. Yeah, it should be 14.4. That's the axle. The answer's over there. Okay, cool. Is everyone happy with this? Any questions with finding the mass moment before we move on? Any questions, guys? Yes, sir, all good. Right. Okay, I just want to check something. Okay, yeah, let me first, Tajrik, I'll get you a question now. I'll show you exactly what's subtracting. Okay, so that's the first part. And then I'll show what Tajrik was asking me. So remember, the objective of the question, like I said to you, we have to find the whole mass moment of the whole assembly, and we have to find the radius of gyration. Or it doesn't really state there, but that's typically. So the total I is going to be, what's it now again? 0.4573 times 2. That's the two wheels. Plus 0.0045, right? So 0.4573 times 2 plus 0.045. And we should get a total of 0.9596 kilogram meter. Our total mass is obviously 22.513 times 2 plus 14.396. And we should get a total of 59.422 kilograms. You guys got that? Yeah, seems our stuff is legit there. What's my total mass moment? They have 0.9191. So make a mistake something. Okay, it's my. Are you guys happy with my total mass moment and my total mass?
Sir.
Yes.
Yes. Why multiply by 2? Are you considering the other side of?
Because remember, it's a total mass moment. So what you've done, this is a mistake here. So I thought, just give me a moment. Let me just remove this. This was 0.9191. Yeah. So remember, we have two wheels. Are you with me? So we found the mass of one wheel, hence times by 2. And we found even, yeah, that's the reason why. So there's two wheels. So you have to times it by 2. That's the reason why I'm timesing by 2. Remember, we're looking, we just did it. I should have said here per wheel, if that was okay. Yeah. We only had two wheels on anyway. Okay. So that's your total mass and total that. And then from that, you can simply find your sum of your that and your sum of your mass, and you can find your radius of gyration. Is it all clear before I? Yeah, thank you, Mr. Silva. Before I get to Tashrik's question of subtracting and so on, it's a very important question actually. And 0.124. So Mr. Silva was on fire. Yeah, meters, 124 millimeters. I think that's the answer. Yeah, 124.4. Cool. Yeah. Is everyone happy with this before I do the percentages quickly? Thank you, Nosipo. It should be as clear as day. I'll show you what to work through as well. I want to see if you can figure it out. Let me have a look here. Fantastic. Thank you, Ms. Mbambisa, Prof. Mbambisa, Professor in Marine Engineering. So percentages is fairly simple, guys. So we're going to say of the wheels and then of the axle. Obviously, we just take the total mass moment, which will be at the bottom. And obviously, we're just dividing it by the individual mass. So for one wheel, the mass moment was 0.45. Oh, so sorry, it's 0.4573 times 2. That's how much the wheels are contributing. And for the what we call this, we're gonna have to do a few of these ones. Well, just to get you used to 9191. This comes up to 99.5%, and obviously this will be 0.5%. So basically taking the total, dividing by individual stuff. So I'm obviously adding the wheels together. So what it means is that the wheels, even though the wheels are aluminium, by virtue of this shape, they're contributing most of the rotational inertia. Isn't that interesting? Mr. Breer, tell me why. Why are the wheels representing 99.5%? Prof. Mbambisa, you as well. So the axle is representing only 0.5%, whereas the wheels are representing 99.5%. Even though the wheels are made of steel, right? It has more mass. Arguably, no, it's actually not more. It doesn't have more mass actually, compared to aluminium. Funny enough, but it also, yeah, but it's also steel. But why do you guys think? Where's an idea? I mentioned it before. The position, yeah, there we go. Because the position of center of gravity from the point of rotation. That's true. It's also that's true. Torque and centrifugal force is greater in the wheels. Yeah, I guess they're all true in a way. I mean, arguably. So I'll question mark that. I'll see if you guys can come back to me with this. So I want to talk to the time. I want to talk to what Sharik asked me. So if we're not going to use this formula over here, right? What we have to do if you want to do subtract, for instance, what Sharik was talking about, subtracting this particular thing over here. So let me just see. So Tashrik want to know if we could have subtracted, subtracted this thing. Tashrik, what we had to do was find the solid by itself. So, and what I mean here, I hope you guys are following me here. You say the mass of the wheel, the solid portion is the whole solid portion, is going to be 2,600 times pi over 4. Let me just quickly see here, times 0.4 squared times 0.07. Right? Just get that quickly. Times 0.4 squared times 0.07. I get a mass of 22,87079 kilograms. If I considered, so I shouldn't call it mass wheel, now I should call it the solid portion, and it's the hollow. I have to now find the hollow portion. So let me just erase this here. Just say M solid and M hollow. So we do exactly the same thing again. So it's 2,600 times pi over 4, and I think that was 50 more, times 0.07, right? So I'm just going to adjust the diameter of my calculator, and you should get 0.35736 kilograms, right? So if I was to do what Tajrik said, I would have to find the mass moment of each one, right? So the mass moment of the solid portion would have been, it's still a complete disk, so it's the same formula, md squared over 8. Oh, man, this button of mine it's actually the new update. The mass would have been 22.8707. The diameter was 0.4 squared over 8. And let's get that answer. Students, are you following? Tajrik, are you there? I mean, you asked this question. And students, are you understanding what I'm trying to achieve here?
I'm following, sir.
100%. So that's 0.45741, right? And kilogram meter squared. And then for the hollow portion, we do the same now. So hollow portion, so I hollow, is going to be the same formula, obviously, and that's going to be 0.35736. And then we're going to have to say 0.05 squared divided by 8. We'll just get that. And you should get an answer of 0.00715 kilogram meter squared. Tajrik, are you happy with that? Just checking our answer here. And to find basically the total, you have to subtract that portion out, Tajrik. So I total would have been the I solid minus the I hollow, because it's not there in essence. So it would have been at 0.45741 minus the 0.00715. And you should come up to the same answer. So I get 0.450. It's quite strange. I don't actually come up to the same answer. Funny enough, it's supposed to come up to the same. Not sure why, if I made a mistake somewhere. But you can also do that. But obviously, if you have a ring, because it's derived from the same principles, let me just make sure my answer quickly. 35776 times 0.05 squared. I'm assuming my math is all right. I made a mistake here. 8. Yeah, it should come out. Oh, yeah, my answer is not exactly the same. I see why. Yeah, I should get. It's not this. Yeah, that's what I thought. There's a mistake here. This is 0.000111675. There we go. That's what I thought. Tajrik, can you just confirm this here? There's 3 zeros there. Zeros 111675. 5741 minus answer. Yeah, you should get this answer. So that's another way of doing that, basically. I'm not sure what this answer is. Just 4572 something. 4572. Yeah, it's right here. There we go. 4573. There we go. Are you guys happy with that? You guys understand what I did there? Like removing that portion. It's the same thing. Yeah. So you are able to do that. Thank you, Mr. Garcia. I hope you guys follow that. Yeah. So this is a typical question. And what is important, my students, is finding the total, obviously I'll summarize it for you. Find the total mass moment, find the gyration, and find the percentage contribution. The extra marks, the marks for the, not even difficult to do, the extra contribution. What's the extra contribution? The contribution of which element to the rotational inertia. So that's what's important there. So let me just close this up. And maybe we can do some more here. Okay, yeah. So let me just share. Cool. Nearly there, guys, nearly there. Okay. So so I'm directed to some examples, obviously, for you to do. Now it's been a mouthful today. Yeah. So this is another classical question, and this is what I was talking about. Just give me a moment. I'll acknowledge you now. Just want to place it there. Okay. Yes, Tashrik.
Yeah, so just before we move on, so this gyration, like, so this distance, where do we reference that from on that wheel with the shaft? Like, where would that distance be referenced from?
Okay, so what it essentially means, Tashrik, just drawing off the sketch here, and it's not that it must be, it's not nothing fancy, man. Let me just quickly show you. So like I said, we basically converted the whole system to a point mass. So let me just quickly sketch that. You never actually auto sketch. So this is this is obviously, let's say, the XX, whatever, the ZZ, the the Z, whatever. And what it means basically is that we're concentrating that whole mass. And what is it mass total to? Just let me just look at the answers here quickly. It's 124.4 millimeters, let's say, and our total mass was it was where was it mass again? 59.42 kilograms. So we're rotating about the X. It's basically like we're making a, it's like a really hypothetical concept, basically. So don't think too much about it. Yeah. Cool. So what's important to me now is actually this part, right? So you're asked to work out the percentage contribution. Make sure you work out for each thing you've done, for each thing you've actually done. So now the other part is asking, determine the torque to accelerate assembly. This is now obviously copied from another question here. From 100 revs to 650 revs per minute in 10 seconds, right? So what we do here is basically we have to find our alpha, because we know now that torque equals I times alpha. So obviously we have to convert these guys into radians. So that's 650. So with all mass moment questions, this will be attached to the end. It's literally 3 marks, but it's just providing some understanding, and the other one is going to be 100. Rick, your mic is still on there. Divided by 60. And then obviously we have to divide this by 10. Then we're going to get our angular acceleration. Cool. And once we have an angular acceleration, all we have to do is times by the total. So let me just get an angular acceleration quickly. Mr. Ford, how are you? Mawande? Padimang? Mr. Padimang Sasha Sima. Great. Sasha. Padimang Sasha Sima. So just quickly get it angular acceleration. So the 2 extra part of the questions, and I will create one type of question like that to play around with. Sasha Sima. Thank you, Mr. Silver. I think it's Dr. De Silva now. She's not wasting time anymore. So 5.76. That's radians per second squared. And all we do is take our total mass moment, which was a value of 0.9191, nearly 1, 0.9191, and we times it by angular acceleration, 5.76. And if you do that, we need a torque of 2.94 Newton meter to produce that acceleration for that mass moment of inertia. Let's see, and if I had to ask for the power, how will we compute the power? So simple, what speed would we use? What speed will we use? Prof Mambisa? So I had to ask you calculate the torque and the power. .550 revs, yes. The Duplessis is right. It's basically the average of the two. Yeah. 550. Why 550? Or 650 you mean? The highest one. Yeah, if you want to be fancy, took the difference. Oh, why would you take the difference? That's what I was thinking. Yeah.
The highest one, yeah.
I would say the highest one because that will require more power for the thing. So that is why, just by the way, I don't typically are you on? Didn't know you were on. You know, because obviously we need more energy to accelerate. So obviously you want to take the higher one. So that's why I don't typically ask the power for these type of questions. You'll see in between voice and haulages and stuff like that. It's a bit more better. So the torque is what I essentially focus on most of the time. In terms of this type of questions. All right. Okay. So guys, we at the end here. So I think what I possibly want to depart on is this particular problem. Yeah. I think it's part of the notes I've sent. And yeah, it is there. Okay, let me just quickly share. Shouldn't we take the final speed? Yeah, I see it's a bit tricky because remember you try to find the power requirement for a particular thing. So let me just quickly share the notes that I've posted. Just give me a moment. All the exercises. Okay, so let me just open it up. And it's debatable depending on what you want to look at, but I'm with you. So you see the problem with the final speed is that's when there's no acceleration anymore. That's a bit of a problem because we need to know how much you require to accelerate the system. But like I said, don't worry about the power anyway. So I'll post this note. Make sure you guys have a go at it. What I urge you to complete is this exercise number 4. Make sure you clap that. This over here. I think those are thin plates over here. If we can do those, I'll be extremely happy. Yeah, that'll be nice for you to do. And then try that. That's your axle. And try this. I'll probably start off for this example next week, because I need probably half the session to actually complete mass moment. But the one thing which I want to see if you're able to do is see the spoke over there. That spoke, it's classified as a thin rod, right? So make sure you're using the right formula for that. But what you're going to have to do is assume the whole length of the rod and then subtract that piece. So I'm just dropping a hint here. Try this for homework, essentially. Homework. There is homework. Do this example. We've got an object made of brass. We've got some interesting stuff happening here, and try to solve this one. But we will obviously do this together. But this is called a spoke. It's like a bicycle wheel or flywheel. And yeah, have a look at this. See if we can do it. Yeah, so I'm just showing you. I've posted on Blackboard. Try to do that. Once you've done next week's lecture, we will continue. So I don't want to bombard you with the rest, because the last part of this particular chapter is something called the parallel axis theorem. And what it essentially means is, or what we use it for, is that when a body doesn't rotate about one of those axes, so it's the axis essentially shifted away. So for instance, rotating and tippling at GG, and then what happens if you're rotating the same body, or what if the main assembly is rotating at CC, for instance, in a case like this. So this whole thing was rotating. That bar over there, we have to find this mass moment of inertia from AA to that particular part over there. So I don't know, we're going to talk about it. So I'm just explaining to you, you know, what this is all about, basically. And then once we're done with that, it's basically, that's the core of, and it's also perpendicular axis theorem, which is not really a big deal. But yeah, that's basically all. So that, we're going to continue with that next week, but make sure you practice those problems. I'm going to try and create a small exercise for you, or maybe a 2-question tutorial as well on top of that and additional stuff. But make sure you're able to calculate the torque. I'm saying that. Make sure you're able to calculate the torque, and make sure you're able to find the percentages of different, you know, the percentage, what contributes the most here. So, okay, fortunately here you have a copper rim on the outside, and you have the hub, which is steel, and the spokes, which is steel. So yeah, so we're gonna see how that goes. But obviously we've got into it. The next week we'll start the mass moment and then simple harmonic motion as well, which is easy but difficult section at the same time, but it's not too difficult anyway. Okay guys, if there's no other questions, if there is any questions, we can go to it, and yeah, you can end the lecture if you guys are happy with that. Cool. Any questions before we conclude? None? Tashrik, Mr. Asa, so do you have notepads on campus? Yes, I have notepads. You were there when I issued the notepads, Mr. Ford. That's in 3.31, or you can get it at the secretary's office. If anyone needs a notepad, please go ask Ms. Nkani. It's there in the office. Or it's in 3.31. There's a whole stack of notepads there. Yeah. If you haven't gotten yet. And you can take power which we should use for, like I said, don't worry about power for these questions. Yeah, so don't worry about power. Just the torque and the percentages. That's what I care about. For instance, just lastly, like you can see there's a table of different densities here. Nothing for me to give you the same question with, you know, I can make the actual steel now, and I can make the wheels, for instance, not the actual steel, the wheel steel, and the actual aluminium, or cobalt, or molybdenum, or titanium. Is titanium even there? Or cast iron, or you know, brass. It's a lot of play around here. But it's important for you to understand the rotation. Look at this one, for instance. I said, what if this assembly? Maybe I should use this one as a tester. What if this assembly was rotating, you know, through the y-axis here? But it becomes tricky, because the reason why is if it's rotating through y, it's easy for the axial, but it's not easy. It's not easy for the wheels, because now we have to talk about the new thing I talked about, the axis theorem, right? So yeah, so we're going to get to all of that. Yeah. So this is just the start, the warm up, do the warm up problems. There's quite a few of them. So yeah. So whatever you can see, try and do it immediately. You know. Yeah, anyway. Okay, guys, there's nothing else. Thank you very much for attending, and just look out for an extra exercise or two, but make sure you do those. It's very important. Keep up with the work, and then yeah, see you on Wednesday. The guys are doing electros. Cheers.